In this problem, we're computing the work done by a combination of two forces. So we have two workers that are attached to this cart with ropes. They're applying different forces, and each of those forces has an angle of 30 degrees with respect to the displacement vector. So there's the displacement vector, and it has a length of 10.5 meters. We're also given the mass of this cart, and we're told something special about this cart. It moves at constant velocity. Now in part A, we just want to get the work done by the combination of these two forces. And you have options here. You can get the work done by each of the forces and then add those together. Or you can add together the x components, in other words, the parallel components of both of these forces, and then compute the work done by the combined force. I'm going to take the first approach here. And I'm going to start by referring to the worker on top as number 1 and on bottom as number 2. And I want to get the x component of the force exerted by worker number 1. The reason I'm taking the x component is because that's the exact direction of the displacement vector, and the parallel component is what we want for computing work. That x component is going to be 520 times the cosine of 30 degrees. And so the work done by this worker, I'll call that W1, is going to be the parallel component of the force, that's 520 cosine of 30 degrees, multiplied by the displacement, which is 10.5 meters. And we get 4,728 joules of work, just rounding to 4 sig figs for this intermediate calculation. We do the same thing for the second worker. Find the parallel component of the force, that's going to be a 410 cosine of 30 degrees. And that means the work done is 410 cosine of 30 degrees times a displacement of 10.5 meters. And this gives me 3,728 joules. So the total work done by these two workers is just given by adding these two numbers together, the work done by worker number 1, the work done by worker number 2. And I get 8,457 joules. I kept a little extra precision in my calculator. Now traditionally I'll round everything to 3 sig figs, so I have 8,460 joules of work. Then part B is really just a concept question about the work energy theorem. So I want to know the work done by friction, and I know this thing moves with constant velocity. And that means there's no change in kinetic energy at all. And so if I look at the work energy theorem, the net work done on this cart results in a change in kinetic energy. But that's 0 in this case. And the only other thing doing work besides these workers pulling with the ropes is the force of friction. So how much work did friction do? It was exactly enough to cancel the positive work input that these workers put into the system. The work done by friction must be negative 8,460 joules. And we're done with the problem. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.